We've been talking about graphical models for several videos now, and at this point you might be thinking to yourself, well, that's all nice and good. You know, you have those sort of simple abstract examples of graphical models, but give me some real-world examples. Are these things really useful for more complicated distributions? And what does that look like? So in this video, we're going to look at a couple non-trivial sort of examples of applications of graphical models. And the first one will be linear regression, and then we'll look at Bayesian naive Bayes. So to be precise here, I should say we're thinking about directed graphical models. There are also undirected graphical models, and they have a slightly different formalism. The rules are somewhat different for undirected graphical models, but you're most likely to come across directed graphical models in machine learning, and so I wanted to introduce these to you first. So our first example, we'll look at a graphical model for linear regression. So you remember in linear regression that the setup is we have some data, some xy pairs, x1, y1 up to xn, yn. And let's say xi is say some d-dimensional real vector, and the yi's we'll take to just be real numbers. And our goal is to model these data and come up with a function. Let me put it down here. So we want to come up with a function f of x to predict new values, and the form of the function under linear regression is w transpose phi of x, where phi is some vector of basis functions and w is some weight vector. So remember, the linear part was linear in w, not necessarily x. So you could have nonlinearities in x through the phi basis functions. And the model that we used was, and I guess this is, to be precise, this is for the Bayesian linear regression. So the generative model is the weight vector w was normally distributed with mean vector 0 and variance, let's say sigma naught, I guess just sigma squared I times the identity matrix. And then each of these y's, yi, is normally distributed with mean w transpose phi of xi and some variance. Maybe I do want to let's put sigma 0 squared for w and sigma squared for the y's. And these are conditionally independent given w. So this is the linear regression model, and we can draw a graph. We can draw the graph for this model. So let's do that. Let's draw the graph. The graphical model corresponding to this Bayesian. Let me put to emphasize that this was our Bayesian linear regression model. The graph is the following. W is some, move it down a little bit. W is some random variable, and then each of the y's is a random variable. We have y1 up to yn, and they're conditionally independent given w. So we can draw that in this way. Let me put one more just to show you the pattern. y2, and so on. So there's just an arrow from w to yi for each yi. And in this video, we're also going to introduce a little bit of notation and terminology associated with graphical models. So an additional notational thing that people do is to put sometimes just a little dot for the parameters. So W depends on this sigma naught squared parameter. And if we had a mean, we could put mu here or something also for a mean of that guy, but we don't need to put that. And also yi, each of these y's, depends on its corresponding xi. So we can denote that by this. And we put a little dot instead of a circle for something which is non-random. It's in some sense a parameter that's a non-random parameter. So this is a graphical model for this setup. Why is this a graphical model for it? Because we can factor this distribution, because the joint, let me put it in some color, the joint distribution on W and all the y's, y1 up to yn, it factors as the probability of W times the product of the individual distributions times the product of yi given W for each I. And that's exactly the form that we needed the distribution to factor into, the joint distribution to factor into, in order for that distribution to respect this graph, right? We have W. Forget about these other things hanging off here for now. We have W, and then we have y1 depends on W, y2 depends on W, and so on up to yn depends on W. So it respects this graph. And let me give you another little, another notation which is useful here. If we were to draw, to emphasize why this is useful, each of these y's I drew little dots for the parameter sigma naught squared and each of these x's, but I didn't draw the one for sigma squared, so we could have put over here like sigma squared and then had an arrow for each of these. But this is starting to get sort of messy now, right? All these arrows crossing. And one nice way to clean up this sort of diagram is to use what are called plates, plate notation. And this same graph in plate notation would be the following. Whenever we have something which is repeated like this, we put it on a plate. So maybe to motivate this, let me draw this. Let's scoot down a little bit. I could put a little box around each of these, y1, y2. I'm going to sort of stack them up in 3D here. y3. So I'm sort of stacking them up one on top of the other, and so on, back to yn. And W has an arrow going to each of these y's. So if you envision this as sort of a three-dimensional stack of these square plates here, and we stack these plates all one on top of the other. You know, if you ever go to like a buffet or something, and you go and you get a plate and off of the stack, and all the plates are on this big stack of plates. That's sort of the analogy here. You have this stack of plates. Each of them has some, in this case, just one random variable. And so we're just going to stack them all one on top of the other, and we'll just look down at the stack from sort of the top. So if we did that, we would have yi, W going to yi, and we would only see the top plate. All the others are sort of underneath. And actually, let me go ahead and let me include the little xi down here. And sometimes people put like n, or maybe I'll put it up here, n to denote the number of plates. So there are n plates here, y1 up to yn, and each of them with its associated xi. And I can just add back these little sigma naught squared. And now, so a nice thing is that when we put this sigma squared off to the side, sigma squared, we only have to draw this one arrow, and we don't have this whole jumble of crossing arrows. So this would be the plate notation for this graphical model here, this graph. And this thing here, so this is called a plate, this square. Now, one other convention I'd like that you should definitely know about is in this setup when we're doing Bayesian linear regression. So we had these random variables y1 up to yn, and each of them had this distribution. We were using those to model the observed y's. But then when we go to make a prediction, we have a new x, so there's a new x, and a corresponding y. We use a new random variable y, which is distributed. So y would be distributed normally, just like this, but with, so I'll just say y would be distributed like this, but with x instead of xi here, and conditionally independent of the others. So if we wanted to add this new random variable to our diagram here, to our graphical model, then let's go ahead and do that. So let's see. We would need to have a new y over here somewhere, and it's got its own little x. I guess I should put an arrow there. And of course, it also depends on this, but let me leave that out for now. I guess maybe to be precise, also depends on that parameter. And now we would like to be able to distinguish between random variables which are conditioned on and which ones are not. So in other words, in our setup here, when we're doing linear regression, we get to observe the values of these y's, right? We get to observe that y1 equals little y1, and so on, yn equals little yn. And when we do our inference, we do the inference conditioned on the data. We condition on the fact that these y's take these particular values. So in a graphical model, when we want to indicate that something is being conditioned on, so for conditioning, let me use a different color actually. Let me use like a gray or something. So for conditioning, we use shading. Shaded random variables are conditioned on. So when we want to say that the conditional distribution respects a certain graph, then we indicate that the random variables are conditioned by shading them. So here we would shade each of the y's, and I guess that's it. Right, we would shade each of these yi's, and those are the only random variables which are unknown. So these are observed random variables. And another little piece of notation here, or terminology I guess, is that a random variable which is not observed and is a sort of a parameter, we often refer to as a latent variable or a hidden variable. So W in this case would be a hidden variable or a latent variable. Okay, so that was Bayesian linear regression. That was the graphical model for Bayesian linear regression. And next we'll look at Bayesian naive Bayes.